Well, welcome. Welcome to another edition of the Tutor Wizard. We're into stream number 7 tonight, lecture number 7. I'm just checking my audio levels, making sure everything's fine. Looks good to me. Let's get back to business. I'm Tim, your host, and you should strap in tonight because we've got a lot of material to cover. In lecture number 7, we are the first of several lectures that are going to deal with probability. Tonight, we are specifically, the wrong one there, sorry, my bad. We are going to concentrate on the normal distribution, how it applies to the concept of chance or probability. That means we're going to talk about z-scores in the z-table. We'll touch on the empirical rule as well. We'll do several problem examples, and we cannot forget that the uniform distribution is a lovely little poster child to understand continuous probability distributions. So this isn't in the precise order that we're going to cover them, but it is the topics that we're going to cover tonight. So I guess we should probably get busy. Let's do that. Go to the next slide. There we go. Properties of continuous distributions. Well, those encompass these 3 points here. I'm going to expand on the material above, of course, but let's talk about this stuff first. So when we talk about continuous probability distributions, and we don't want to talk about calculus too much because not everybody's done calculus. Not everybody is expecting to do calculus, although some people will. The uniform distribution is essentially a rectangle. Looks like that. You start here. We'll call this point A. We'll call this point B. And of course we have some height value here. Now, area for this is exactly 1.00. And this parallels probability. Probability is always a positive number, right here. It ranges between 0 and 1. 0 means something's not going to happen. 1 means it will happen. So the area below this line, which is a function line, and above the x-axis is exactly 1. Now, uniform distribution, of course, is this lovely little rectangle. The normal distribution is the typical bell curve that we associate with statistics quite often. Looks like that. But the area is exactly 1. Now, the mathematics of finding how much area is in a particular region for this particular distribution is quite complicated, and we're going to use tables for that. So we'll set that aside for now. But the area for a uniform distribution, this guy here, is quite easy to get because remember, area is simply length times width. And that tells us how we can find out what the heck the height value is. Right now, we don't know what the height is. So I'm going to show you how to get this. And the reason I'm talking about this one is I know there's going to be a question or two that's going to pop up on your midterm, and I know it's on the online homework, specifically for the university that I work at, but it makes a good question to see if you actually understand these things. So if area for the uniform distribution, let's make that little come down here like so, okay, is going to be the width of whatever interval you're interested in times the height. We don't know the height, but we know everything else. Area has got to be exactly 1, and the width is going to be b minus a times height. So as you can see, a little bit of algebra means that 1 over b minus a will give us the height. I'll illustrate this with an example. Now, let's move this page a little bit so we have a bit more room to tinker with. We'll come back up here in a minute. That should be fine there. Okay, so let's say we have a uniform distribution, looks like this, and we start at, say, 2 and go to 6. Now remember, the area in here is 1, right? Well, we have this formula here. So the height, in other words, how tall this thing is then, is going to be 1 divided by 6 minus 2, which of course is 4. So we get 1/4, or 0.25. Now that's pretty easy. Now let's say we wanted to know the area, or the probability. So remember, in this context, they're the same thing. Let's get that out of there. Let's say I'm interested in what's the area between 4.5 and 2.8. So I'm interested in what this area is, because that's going to be directly analogous to the probability. Now, since we're directly analogous to the probability, it just means we have to find out the area between 4.5 and 2.8. And then we're going to, of course, remember area and probability. We're going to do it over here. So the probability will be width times height. So the width then will be 4.5 minus 2.8, and we're going to multiply it by the height, which is 1/4, or 0.25. Okay, so what do we have here? This is 1.2, 1.7 times 0.25. So what's 1/4 of that? Well, it should be about 4.5. 0.45, I believe. I have my calculator here. We'll do a quick check, because sometimes it looks good, but it's not. 0.25, and that's 4.25. I missed a little bit. Not too much, just a little bit. However, we should get it right. So that's the probability. So if the question is asking, what's the probability of some randomly selected value that follows a continuous uniform distribution lands between 4.5 and 2.8? Well, that means it's 0.425, or 42.5% chance of that happening. Now, notationally, we could have written that as, what's the probability that some random value x is less than or equal to 4.5, greater than or equal to 2.8? Well, the answer is right there. It's that. There we go. Then there's our x. Bazinga. Now, the same idea applies to the normal distribution, the bell curve. Of course, the problem with that is you need to know calculus to figure that value out, but that's why we have statistical tables, and we're going to beat the heck out of that idea here in this lecture, so just be patient with that. Let's move this down a little bit. I want to comment on a couple things. Okay, so we know that area then is exactly 1, and we also know that area is width times height, if you need to do it by hand. These are always positive values, and those positive values range in the context, or in the language of calculus, these are closed intervals from 0.00 to exactly 1.00. So you're never going to have negative probability. So far, so good. Now, what is this business about no discrete value? Well, I should have maybe worded this a little differently, but what I'm saying is you will never see, well, if you do see this, and this applies to uniform and the normal distribution. Let's say, what's the value of x is equal to 4 exactly? 4.00. Well, this is always going to be 0. You don't even have to do any complicated computations. You don't need to look anything up because equality implies a discrete value or a distinct value, and you can't have that. The answer actually is, maybe I shouldn't have said discrete value is forbidden, but discrete value perhaps would have been better worded as 0. The probability of a discrete value is 0. And I'll explain why. Let's go look at our pictures here. Let's move this down a little bit. Let's look at the normal distribution one, the bell curve one. So let's say, as an example here, we'll use x is equal to 4. Let's say this is x is equal to 4. But we also know that probability is width times height. Well, we know then that the height is this value, whatever that happens to be. And you can get a height value depending on how this is presented. Some tables or some graphs will give you a height value. But how wide? What's the width? Well, that's the problem. The width here is 0. And 0 times anything is 0. So what we have then, for the probability of x is exactly 4, we're going to have some height value. It's non-zero. We can see that. But we're going to be multiplying it by something that has no width. So we get 0.00. So, if the probability distribution is continuous, equal signs don't matter. Now you're saying, well, that sounds a little fishy. Well, equal signs, as I've written for x is equal to 4, don't matter. Well, I should say they don't matter. They evaluate to 0, but what I'm really getting at is, let's look down here what I wrote. Here I have less than or equal to. Here I have less than or equal to. This is what I'm talking about when I say equal signs don't matter. This could equivalently be written as x is greater than 2.8 and x is less than 4.5. So whether there's an equal sign included with the inequality or not makes no difference because there's no width associated with that equal sign. So don't worry about getting it wrong because the notation switches from, say, this style to this style. If it's continuous, the two things mean exactly the same thing. And this applies to all continuous distributions that we're going to encounter in this course. We only have a couple of them, not a lot of them, but just keep in mind that for continuous distributions, it's width times height. And if anybody tries to tell you that there is a non-zero probability when you say that the random variable is exactly equal to some number, well, the probability of that is 0. And that's all there is to that. Let's move on. We're going to spend most of the, well, who's kidding who? We're going to spend the rest of this conversation talking about the normal distribution or the bell curve here. So the bell curve, let's look at the picture first, then we're going to talk about some of these other things. The bell curve has a center, and it is labeled mu. Now that's a stylized Greek letter. It can look like an M, or it can look like a U. Doesn't matter. Call it whatever you want. So this is the center. If we have the standard normal distribution, then mu will be 0. If it's just a normal distribution, mu will be some value. We also have a spread, which is sigma. And that's also what's known as our standard deviation. So the spread is how wide this thing is. Okay, easy peasy, right? Now, remember, area is exactly 1. We don't worry about knowing the height of this thing because, while there are ways to figure that out, we don't need to know it in this course. That's what we have tables for. So this height, if you were to take the equation for this and sketch it out, or run what am I trying to say here? If you were to graph it, it would be very, very small. Not much height to it at all. Because remember, the area is restricted to exactly 1. Now, notation, we can call it the normal distribution, or the mathematical shorthand looks like this. Capital N represents normal distribution. Then we have the center, and then we have the spread. So an example then, if we're talking about a population that has, say, a center at 5 and a spread of 2, we could write it like that, although usually we don't include the symbols. This would be more compactly written as 5, 2. So that means this would be 5, and the spread would be 2. Now, typically how that's notated, let me get rid of some of this stuff here. Let's redo that. There we go. So the typical notation for this then, we would write mu is equal to 5 and sigma is equal to 2, and that describes this bell curve. So watch out for that. Now, there's a formula associated with this curve. We're going to make extensive use of this tonight, and that is this fellow right here. The z-score is what we're going to be seeking. I want to illuminate this somewhat. What is this y? Here's that Greek letter mu, and here's sigma. So this letter here, this will be a value that you are given that you're interested in comparing to a known value. So this is known. This is also the population mean. Population mean value. This is the value of interest. We want to compare the two. How do we do it? We subtract one from the other. And this is the spread. And this also leads to a conversation about, what we're really doing then is standardizing. We'll talk about standardization more later, but the point is you're always going to be dividing out the standard deviation. Let's call that STD dot DEV. There we go. Oh, I just spotted a typo. Oh, man. Okay. I went through these earlier and go, I got no typos, and then I've got a typo. So look at that. Let's fix that from lack of embarrassment. Interpretation. We need a T there. There we go. Woot. And my marker back. So how do we interpret this? Well, I've largely talked about that. Y is the value that you're given that you want to compare to a known value. But before you can use a table, I'm going to talk about this just in a moment, we need to divide out the spread. Now here's the thing. And no one's going to ask you why, so I'm not going to write down anything. I'm just going to tell you why. Because there's an infinite number of populations that you may be interested in studying. And for every one of those infinite number of populations, there's probably an infinitely large number of values you want to compare to the value of the mean, which means you'd have to have an infinitely large set of tables to compute the probability or the area. Well, that's not doable. The alternative is to do the calculus computations individually every time. Well, that's tedious and you don't want to do it. So we standardize by dividing the standard deviation, because what we're doing then is reducing every problem from that infinite set of problems. We're reducing them down to a common yardstick, a common measurement. And that process is called standardization, which then allows us to use two tables, one for negative, one for positive values of z, and then we can look up the appropriate proportion or probability, which word depends on context of the problem. Let's go back up here to our picture for a minute. All right. Pardon me a little bit. The tree in my backyard is in full bloom right now and smells great, but I'm a little bit crouped up a little bit tonight. So my voice catches a little bit. It's due to pollen. Okay, so what am I talking about here? Well, here's center. Now, let's get a marker here. Let's use red for this one. Now, let's say I am interested in a y value that is larger than 5. Let's say it's 7. So the question might be, what is the probability of y being greater than or equal to 7? Well, that means I'm interested in what's the region here. Since we're greater than, I'm interested in this right tail. The probability then will correspond to how much area lies below the curve, below this thing, right? And to the right of the vertical line. And I'm going to get to that. The problems we're going to do tonight, I'm going to show you how to do that. Now, maybe the question was, what's the probability of some y value being less than 2? Okay, well, where does 2 go? Well, 2 is smaller than our center at 5, so 2 might be over here. So we'll call this y is equal to 2. And since we're less than or equal to, I'm interested in this region. And again, this will be a table lookup. What are we going to be looking up? We're going to be looking up z-scores. I'm going to write them in here. I'm going to show you how to do this as well. Z-scores, then, come from using this formula. So for the first one, let's get a little bit of room to write here. Just a little bit, not too much. There we go. Okay, so here, I'm going to have z is equal to, so I had 7 as the value for y. The mean was 5, and I'm going to divide out the standard deviation, which was 2. So this is equal to 1. So that means the value here, this is z, is equal to 1. Now here's a key point. This is an exam question to see if you know what the heck you're talking about, if you've been paying attention in class or not. What does that 1 represent? That 1 that I wrote right here, 1 standard deviation means, with z equals to 1, means the distance from the center to this value is 1 standard deviation greater than the mean. That's all it means. Z is a number that represents the number of standard deviations you're either greater than or less than the mean value. You need to know that. You're going to get asked that. Now, if we do the other one, the one on the other side, well, clearly, I'm going to be going z is equal to 2 minus 5 over 2. This is negative 1.5. At least it better be. So that means this is a negative region. Now, there's another piece of information, right? That means any area, any region to the left of the center has a negative sign on it. Any region to the right of center is a positive sign on it. Now this means this gap here is 1.5 standard deviations smaller than the mean. That's how far out to the left our observation of y is equal to 2 ended up at. Now, of course, I haven't told you how to turn those into probability yet, but that's what we're coming to. We're going to have a lot of practice tonight on how to turn these regions into probabilities without having to use any advanced mathematics. So what you see here is essential for a big chunk of this course. Because later on, when we get into hypothesis testing, in other words, inferential statistics, we're going to modify this Z formula so that instead of just a singular y value, we'll have an average y value. That means the denominator is going to change a little bit. Plus, we'll also be using a couple of other formulas for different contexts. And the idea throughout it all remains the same. There's nothing that I've shown you here that you need you're going to be able to forget between now and the end of the course. This will be with you for the rest of time, which isn't necessarily a bad thing. Okay. I think we should maybe move to the next slide, because I don't want to... There we go. Haven't got to the Z table yet, but we're getting there. So there's our formula again. Now, you'll notice the shaded region. I'm looking at this table, by the way. That shaded region, when we get to the tables, all the decimal values in the tables, and I might as well show you, hang on. There's a table. We're coming up to it, okay? The p-values. P stands for probability. It can stand for percentage and it can stand for proportion. Point is, that's another p word, the table values give you the region to the left-hand side of wherever your z-score lands. Your z-score is right there. The z-table then, for positive values, when I say right side here, I mean positive z values. The p-value then will be talking about this entire region. But we also have a negative region here. And again, p-values will talk about the region to the left. Now, that's all well and good, but what do you do if you need this region here? Let's put a different color in there. What about this region? How do you get that? Well, that you get by going 1 minus the p-value. That'll give you that region there. Now there's a shortcut. You don't have to go 1 minus for that. You'll notice that if you pay close attention to this, this is a symmetrical curve. The left-hand side of the curve here and the right-hand side of the curve are exactly the same. And that means the regions in the tail, a tail region like here, for instance, is mirrored over here. So if I want to know what is the probability of, say, Z being greater than 2.00, I should know that one off the top of my head. If I want to know the probability of that, I can do two things. I can do a table lookup. Well, let's do that table. Okay. I don't want to get too far ahead of here. Table lookup for 2.00. What the heck? We might as well do it. Okay, let's bump over here. Now you'll see, I don't have quite the... I need to move this a little bit. Okay. Now, where's my highlighter? I need my highlighter for this one, I think. Now, 2.00. So this is the z-score. Here's z is 2.0. Second decimal is here. So it's 9772. Okay? Let's go back. I'll give you a better explanation in a minute. So that means this region here, whoops, is 0.9772. But I want to know the area to the other side. So if I go 1 minus, then I would go 1 minus 0.9772, which is 0.0228. That's the table lookup way and the arithmetic way. The other way is to look at its symmetric opposite. What's the other word? Conjugate value, I suppose. If I was to look up the probability of z being less than -2, I will get the same value. Let me show you. You won't take my word for it, because you shouldn't take my word for it. We should always check these things. So let's go to -2. Oh, sorry, I don't want to do that. My bad. Let's do this. -2. There we go, right there. Get my highlighter back. So here's -2, and there is negative, the result, 0.228. So what I'm getting at is every pair of numbers, where the number's the same, the sign is different. So like 2 and negative 2 add to 1. So you can use the rule for complements, which we're going to encounter in more probability coming up. These will always sum to 100%. Let's back up a little bit here. So then we can just look up negative 2. Oh, I'm using the wrong one again. Let's do that again. Let's see. Negative 2.00 is also 0.0228. Yoink. Same thing. All right. So we should talk about that table quite a bit now. Let's do some practice with that. Now, let's see here. Do I want to keep using green? Anybody problem with that? Let's go back to blue for a bit. So let's say I want to look up, I want to know what the probability of z being less than or equal to negative 1.00. I already know this one. This one comes up all the time. Well, this should be 0.1587. So that would be like saying this value here is negative 1.0. So one standard deviation below the mean. Well, let's check that. Let's bump ahead to, and let's go back to Mr. Marker. Okay. Here is negative 1.00. And there it is, 1587. That's the area to the left. So if I wanted to answer the question then, what is the probability of a observation producing a z-score of negative 1.00 or smaller? My answer is this. Easy enough. Let's try another one. How about this one? P, how about z is greater than 2.52. Okay, so now I got that second decimal in there. And now we'll see how the table works for that. Let's go and take a look at that. That's positive 2.52 at the, okay, so here is 2.50. This is 2.51. So this column then is 2.52. So we get this, 9941. Let's go back. Well, now wait a minute. I want to know greater than that. So I got to go 1. It didn't change pens again. Let's try again. 1 minus, what the hell did I say that value was? 99 something something Batman? 9941. There we go. So this works out to 0.0059. So that's just a little bit more than 1/2 of 1%. Now remember, I could have done this the other way. I could have looked up negative 2.52. Let's do that. Check. Z is equal to negative 2.52. And what do we get? Let's find out. Next page, next page. And I got to move that one a little bit. There we go. Marker. All right, so here's 2.5. We need more room. No. There we go. All right, so 2.5. There's negative 2.5, 0, 2.51, 2.52. There we are. Get that out of the way. There we go. 0059. So this is what I meant when I said you could use complements. Either one will work. Moving on. There, let's not move on too far. I want to do something else here. Back up. All right. Now, here's a more complicated one, and you will get this question on homework and on exams. Let's see here. What is the probability that Z is greater than, we'll keep these both on the positive side this time, greater than 1.0 and less than 2.72. Now I've given you two values. I've got a lower bound and an upper bound. Probably want to sketch that. Let's do that. It's always a good idea to sketch things when you're not sure exactly what to do. So remember, the center is here. Now, when we have standardized values, the center is 0. Okay? Our lower bound was 1. Let's change ink. Go to green. So this is z is equal to 1. And then out here, we have z is equal to 2.72. And we're interested in this area. This will answer our question. Now, I know we have ads running here. They'll let this wrap up before we jump in. I've got a 30-second ad. That's fine. So what we're going to do to answer this question, I'm just going to sketch this quickly. Move that up a little bit. Okay, we're back. I just sketched out the problem. So when you're not sure what's going on, it doesn't hurt to make a sketch. It'd be actually very wise to make a sketch. So here's the upper bound, z is equal to 2.72. Here's the lower bound of z is equal to 1.0. I'm interested in what's the area contained in between these two values. So what we're going to do is we're going to look up the p-value for 2.72, and that's going to give me all this area all the way over to the right. And then I'm going to look up the p-value for z is equal to 1.00, and that's going to give me the value all the way to the, did I say to the right? All the way to the left, all the way to the left. And then we're simply going to subtract the two. So let's do that. Now the way I have this written, it's a bit confusing because technically I'm going to put the big value here and the little value here, and that's not going to work. So let me fix this up a little bit. I don't like the way that's setting up for a big confusion. And let's go back here. Okay, so this is going to come down. Then we're going to go this way. Okay, there we go. So we're going to get a p-value for that one. I should change ink for that. Let's put a red one in there. So this is what we're doing. Here's the upper value, the bigger number. And then for the lower value, we'll leave it as green. And we'll subtract. So remember, this is for z is equal to 2.72. This is for z is equal to 1.0. Now we've already figured out the 1.0. I already did that one earlier. We know that this is 1587. But for 2.72, we need to look that up. Let's do that. So 2.72, and so here's 2.7. That's my eraser. I don't want that wrong one. So 2.7, 0, 7, 1, 7, 2, 99, 67. Let's put that in. 0.9967. So now when we subtract these values, 7 minus 7 is 0. 16 minus 8 is 8. Then we have 8 minus 5 is 3. And we get that. So the answer here is 8380. Or if the question was asking, well, what's the, well, that doesn't make sense. I know what the problem is. You know why this doesn't make sense? Remember, the whole area here has got to be 1, right? Whole area of the in the curve is exactly 1. There's no way this is 83.8%. And that little chunk here, not a chance. And that's because I made a mistake. Let me fix the mistake. Should be 3380. The mistake is here. The 1587 was the area to the right, but we're not interested in that. Remember, with these curves, half the curve is to the left, half is to the right. That means there's 50% here and 50% here. So this should have been 6, 5, 8, 7. And now we'll get the right answer, which should be 33, whatever it was. So this is 0. This is still an 8. Now it's that. And 9. There we go. That's the correct answer now. So this is right. That's how we use the Z table. Let's do some problems with this now. We'll use these tables, of course. I'm going to slip ahead here to where I have my problems. So here's the first problem. Let's set this up a little better for, whoops, that's not what I want. Come on, you. I want to get this page so we have room to doodle. There we go. Now, back to red. We're going to use the same setup. I'm just going to change some numbers as we make our way through here. We are told we have a normal population of objects being produced. Now, the key thing is that I've already mentioned, I have said that the population is normal. This is important, because if you're not told that the population is normal, you got no business using the Z formula until we get to another point in the course where we have some criteria to check these things. So the fact that it's a normal population tells me that I can use this formula. So this is correct. Now, a mean of 20 millimeters, well, that's the value of mu. Standard deviation of 4 is the value of sigma, and the value we want to compare is down here. So I recommend, let's go back to blue. Actually, I read it's a bit weak. While you're learning this topic, I suggest the wise person will sketch this. Once you're comfortable with the whole idea, you don't have to. It's just that it tends to make things a little easier when you can refer to a picture. Okay, so remember, the center is mu, and the population mean is 20 millimeters. And I'm told the population standard deviation is 4. So this is center. This is the center value, this is the spread value. Now, we are interested in what is the chance of obtaining a randomly selected object smaller than 15 millimeters. Well, 15 millimeters is smaller than 20, so that's got to be over on this side. So we'll write this as y is equal to 15, and the probability, in other words, the area that we're interested in, I'll use red for this, is this region here. This is where we're going to get the answer to our question. Now, how do we get it? Well, we use this formula, this one right here. So we're going to standardize. We have y. No, we don't have y. Well, we do have y, but not in that spot. This is supposed to be a z. Okay, so z is equal to the value of interest, 15, minus the mean of the population, we're given that, and divide by 4. So this is negative 5 over 4, which means the z-score is negative 1.25. So we'll write that here. Now that means the value of y is 1.5 standard deviations below the mean. And we want to know what area, the p-value, that corresponds to that. So this is a direct lookup because this is the area to the left of z. We just have to use one of the tables. And we want to use the negative one. So we want negative 1.25. So here's negative 1.2. This is 0, 1, 2, 3, 4, 5. So our answer then is this guy right there. That's kind of dark. Let's get that out of there. There we go. We're interested in that. 1056. That's our answer. So let's go back and write that in. 0.1056. That's our p-value. Pretty easy, isn't it? Darn right. Let's carry on. Let's move on to another question. Same population, same curve, same center, same spread. Again, normal population. Mean is 20, standard deviation is 4. Now, what's the chance of obtaining a randomly selected object that's greater than 28.2 millimeters? Let's make a picture again. Your pictures don't have to be perfect. Mine never are. So the mean is 20. Sigma is 4. But now we're bigger. So we're out here. This is y is equal to 28.2. And we have to find the z-score, because it's with the z-score that we'll be able to find this region here. This is what we want to know about. So let's get that. So we have z is equal to 28.2 minus 20 divided by 4. So this is going to be 8.2 divided by 4. And what in the heck's that going to be? That's going to be 4,025, I believe. No, it's going to, when we say 4, that's going to be 2.05. So that means we're just slightly larger than 2 standard deviations greater than the mean. Now what's the p-value for that? Now remember, this is a region that's to the right. I have 2 ways to get this. I can get this by doing the 1 minus, which is what we'll do first, or then I can look up the complementary value. So 2.05, and it's positive. Let's write this here first before I lose track. Okay. Let's go back to the z table. So at 2.05, let's get the highlighter. So here's 2.0, 0.0, 0.01, 0.2, 0.3, 0.4, 0.5. 9798, that looks like. I got a blob on there. 9798. There we go. And that should give us a p-value, a very small p-value. Let's 9798. Right, let's go back over here. One minus 0.9798, and that is 0.0202, which indeed is a very small p-value. Now the other way to do that would have been look up negative 2.05. Let's write that down as check negative 2.05. Back up. All right, there's negative 2.05 right there. We want the highlighter for that. There's our number, which means we've got it right. Now, barring an arithmetic mistake earlier on. Now, here's a little catch. Let's say there was a production run of 500 of these objects. And we wanted to know how many of these objects, how many of the 500 were larger than 28.2 millimeters. Let's write that out. Let's move this around a little bit so we got some room to write. So this is an accessory question. Ancillary, supplemental, there's a good word. From a batch of 500, how many are larger than 28.2? Well, that's where we use this, because remember I said p-values stand for proportion, also stands for probability and percentage. So we're going to go 500 times 2 hang on, I was thinking percentage there. 0.0202. Well, we can do it by hand, but I'm going to use my calculator because it's more fun that way. 500 times 0.0202 is 10.1. Now, we're talking about discrete objects, so you can't have 1/10 of something. So how I would answer this is I would say 10 or 11. Most likely it would be 10 because 0.1 is closer to 10 than it is to 11. And that's how we would answer this question. And this is that second step that oftentimes crops up on questions that catch students. They get in the habit of, well, I got the p-value, now I'm done, but there's a second part. So I just wanted to remind you to watch out for that. Let's move on to the next question. From the same population, what's the chances of obtaining a randomly selected object that's smaller than 21.51 millimeters and larger than 19.34 millimeters? So this is, we've already seen how to do this earlier when we were just practicing with z-scores in the z-table. We're going to draw a picture and we're going to do the math in the same manner that we did earlier. Smooth this up a little bit. Okay. Now, remember the center is here, and that is 20. I always label mine like this, and sigma is 4. Now, 21.51, we'll call this value, and 19.34 is on the other side. We'll call that over here. So what it turns out then is we are interested in this region. So how we're going to get that is I'm going to find the p-value, the area, heading from 21.5 all the way to the left, and then I'm going to find the same for the other value heading to the left, and we're going to subtract them. Same as we did before. The only thing about a question like this is there's two computations. So let's do them. So here we have z upper. So the upper value is 2151 minus 20 divided by 4. So this is 1.51 over 4. So that z-score is something. The heck is that? It is, I wanted to write this out, 0.377, where did you go? I already wrote this one out, 5. Now remember, the z-table only gives you 2 decimals, so that means you have to round. So this is going to be 0.38. That's what we have to look up. Let's write that here. Okay, let's go look that area up. Previous. One more time. Okay, we want 038. Let's use yellow this time. So here's the 03 line. Okay, that's a real mess. Let's try that again. Okay, trying again. That yellow might be a little weak. Let's see here. Okay, we're using green. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8. 6480. Right there. 6480. Let's go write that down. Boom. That's the wrong color. Let's try again. 6480. Got that one. Now, we need z for the other one. Let's find z lower. Handwriting's getting worse. About almost time to call it a night, I think. So this is 1934 minus 20 divided by 4. So that is 66, negative 0.66 divided by 4. And this is another one of those that's going to give us a requirement of rounding by the looks of it, 0.164. 5. Negative. Don't forget your negative sign. I'm just going to verify that. 0.66 divided by that. Yeah, 165. There we go. Cool. All right, so this is going to round to negative 0.17. Now well, let's label that. That's this one here. Now let's go and look that up. Now back to the highlighter. Negative is there, 0.1. So this is, well, we can do it this way. This row, this column, 4325. Looks like 4325 to me, right there. 4325. And that means our answer will come from subtracting those values. So this will be a 5, 8. I always moved one over from there. So that's 7. That's another 5. That's a 1. And that's a 2. So the answer is 0.2155 is this region here. And that's how you do that question. Now, there really is only one other way these questions can come at you, and this is probably the hardest of them, so I'm going to do it twice. I'm going to find the smallest 9%. So I'm looking for the size now. I'm not looking for the probability. I'm not looking for the proportion. I'm being asked what size of objects represent A, the smallest 9%, and B, the largest 5% of production. And this is also an exam question. And this one is kind of important to have a good picture. Okay, I want that in a different color. Let's try that. Back to blue, please. Okay. Okay, that's the worst one I've drawn yet tonight. So the smallest 9%. Let's do this. Habits are good. That's 20, and this is 4. Okay, smallest 9%. I need to know what the y value is. That's what we're asking for now. That's what's different about this. We're finding the y value, not the p value. So the smallest 9% then would be this area here. I'm told this. That's what the information told me. But what I don't know is this. The largest 5% then is on the other side over here. And again, the largest 5% would represent this tail. We call these tails, by the way. And we want to know what the y value is that represents that. Now, the value here at the top on the right-hand side has a complication. Try to find the largest 5%. You may get tangled up. Largest 5% means this region is 0.05. Then that means everything over here is 0.95. Keep that in mind. We need that. This thing here at 0.09, we don't need to worry about. So let's do the one we don't need to worry about first. Let's do the lower one. So the first thing you have to do with a question like this is find the z-score that corresponds to 0.09. So the first thing is find z. Let's go back to the table. Now that's on the negative side, so we want the negative table. Now what you have to do, I'm going to get rid of all these annotations. There we go. We need to find inside the table 0.0900 or as close to it as we can get. And that is sitting right here. There's 0.0901. That's about as close as we're going to get. If you have software, you can look that up. It's easy to do then. So what are we doing? So what row are we on? We are on negative 1.34. So what we're going to do is we've got to go up here, and then we got to go out here. There we go. So our z-score for this one is negative 1.34. Let's go back. Now, a little bit of algebra. We have negative 1.34 is equal to y. We want to find that. We know mu is 20, and we know sigma is 4. Now we solve for y. So we get negative 1.34 times 4, and we're going to add 20 to get the y value. I'll grab my calculator and we'll just do that really quick. The way to verify that you haven't screwed up, because you can lose the negative sign, because we're on the left-hand side, whatever the answer is, it's got to be smaller than 20. And I get 14.64, which seems to be quite reasonable. Let's double check. I got that right. Yeah, that's it. Okay, so this y value here then, let's get rid of that. That y value right there is 14.64. Now we can do the other one. We want to find the upper. Well, we need, the mistake, well, you could do it, but I'm not going to talk about it too much tonight, is to look up 0.05. But that's going to be on the negative side, and that's not what we want. We want to be on the positive side. So remember, this region here is 95%, or 0.95. So we need to look that up on the positive z table. Let's clear that off and move this down a little bit. And back to our highlighter. So somewhere in here, in the middle, we're going to find 0.95. So here's 94, 84. Here's 94, 95, 95. Now I wanted to point this one out. Look at these two. These completely bracket the value we want. 9405 is too small, and 9505 is too large by the same amount. So what you can do when that happens is take the average of the two z-scores. So let's do that. So here's the lower one. So we're on the line 1.6, 4, and 1.65. So what you can do is go 1.64 plus 1.65, divide by 2, and take their average, and you'll recognize this is a commonly occurring number. The z-score we want is 1.645. And you're probably going to have to do that, so that's why I wanted to point it out. Let's go back up and answer our problem now. And here we are. Okay, got our pen, right? So we get 1.645 is equal to y minus 20 divided by 4. So 1.645 times 4 plus 20 gives us the required value. Let's figure that out. And we get 2658. And that's our value. That's what we want. So 26.58 is the value, the size that delineates the upper 5%, and 14.64 is the size that delineates the lower 9%. You're going to get a question like that on your exam, certainly on your homework too, and that's how you do them. So this is just the first of several of our lectures now that will deal with probability. This is specifically using the standard normal curve, the normal distribution curve, and the Z formula to compute probability. There are several more topics in probability that we need to talk about, and those will follow in the next. I'm thinking we have at least 2 more lectures on probability. I'm not entirely sure what day we're going to do that, but it'll be probably on the weekend, so maybe 2 days from now. And that's where we're at. So in the meantime, folks, thank you for staying with me for this somewhat longer stream today. Actually, we did all right, a little bit more than an hour, not terribly bad. So thank you so much. Hopefully this helps you with your homework and your understanding, and we will talk again in 24 to 48 hours, I would think. Have a great day. We'll talk to you soon. Bye-bye.